We are starting with a new chapter. Before that, I would just like to test your knowledge. What is the smallest unit of a matter? It is the atom. So, atom is the smallest unit of a matter. So, in this new chapter, Structure of Atom, we will be studying about the discovery of electrons, protons, and neutrons. Also, we will be studying about isotopes, isobars, and isotones. We will also be studying about the Rutherfords atomic model and its drawbacks. First, we shall study the discovery of electron. Electron was discovered in the year 1897 by J.J. Thomson. Electrons were discovered while investigating the cathode rays, and it was found that the cathode rays, they were a stream of very small negatively charged particles, which are about 1837 times lighter than a hydrogen atom. And this particular negatively charged particles, they were present in all the atoms. Later, these particles were named as electrons. Here is a picture of how a cathode ray tube looks like. Let us now watch a video to understand how the cathode rays are generated.
Cathode ray tube. Discovery. William Crookes discovered cathode rays when he was studying electrical discharge in gases, whereas J.J. Thomson discovered that the cathode ray consists of negatively charged particles called electrons. Production. Cathode rays are produced in a discharge tube. Hence, the discharge tube is generally referred to as the cathode ray tube. The cathode ray tube is a partially evacuated glass tube with cathode and anode placed at the ends of the tube. A vacuum pump is used to partially evacuate the tube. The cathode is connected to the power source with the help of a clip. The tube is supported on a stand. It was found that electric discharge through gases took place only when the pressure inside the tube is lowered and the potential difference between the electrodes was high. To produce cathode rays, high potential difference of 10 kV to 20 kV is applied between the electrodes and the pressure is reduced to 0.0001 millimeter of mercury by means of a vacuum pump. A glow is seen on the walls of the glass tube. The bright fluorescence glow is due to the striking of the rays emitted by the cathode. These rays are cathode rays. Properties of cathode rays. Cathode rays travel in straight lines. When an opaque object is placed in the path of the cathode rays, a shadow is cast on the glass wall opposite to the cathode. This shows that cathode rays travel in straight lines. Cathode rays consist of negatively charged particles. The rays deflect towards the positive plate when the tube is exposed to an electric field. This is because the negatively charged particles in the cathode rays get attracted towards the positive plate. Cathode rays are deflected by the magnetic field. When the tube is exposed to a magnetic field, the cathode rays follow a curved path showing that they are deflected by the magnetic field. Cathode rays produce X-rays when they impinge on a metal with a high atomic weight. Cathode rays travel with a high speed almost equal to the speed of the light and hence possess kinetic energy. When cathode rays are made to fall on a paddle wheel, a wheel starts rotating, showing that the rays possess kinetic energy.
So this video here by Tutor Vista has given us extra information regarding the discovery of electrons. Next is the discovery of proton. Now proton was discovered in the year 1911 by Ernest Rutherford. He was carrying out the experiment of scattering of alpha particles using a thin gold foil. When he was carrying out this experiment, he observed that there were few alpha particles which bounced back, and from this observation he concluded that there is presence of massive and positively charged nucleus inside the atom which causes these alpha particles to bounce back. Here is a video which shows the construction for the scattering of alpha particle. This is the apparatus for the alpha scattering experiment. So you have a box here which is the source of alpha particle. Then you have the gold foil which is there placed inside the detection screen, and the two slits here, they are made up of lead. The procedure to carry out the experiment. The alpha particles, they are placed inside this box, and there is a small slit. Slit means a hole through which the alpha particles will be coming out. You can also say it as the cross section of the alpha particle. So you can see the alpha particles, they are emitted now. They are passing through the lead plate and then finally through the slit that is there in the detection screen, and then getting bombarded on the gold foil. Now, when this experiment was carried out, it was observed that the alpha particles would scattered at different directions, and also some particles were getting bounced back, as you can see here. Let us now watch another video to understand why exactly this happens.
Rutherford's gold foil experiment gave him interesting results. What results did he get, by the way? Let me recall them for you. He found that most of the fast-moving alpha particles passed straight through the foil and hit the detector. However, some particles got deflected by small angles. And lastly, to his astonishment, few alpha particles also rebounded. Now, how can this be possible? These three observations made Rutherford think that the plum pudding model is not really correct. Let us take a simplified example to understand the inferences first. Let us imagine that we have a ball made up of cotton. The cotton in the ball is very sparsely distributed and has an extremely tiny circle or sphere located at the center. This sphere is quite hard and dense. So hard that it can even resist a bullet shot against it. Now, what will happen if you shoot many bullets across this cotton ball? Most of them will travel straight through the cotton surface. What will happen if a bullet hits the edge of the central heavy mass? In this case, the bullet will slightly change their path and get deviated. So looking at the size of the central mass, it's obvious that only some of the bullets will get deviated. Lastly, what happens when a bullet hits the center directly? Needless to say, it will bounce back, because we know that the central dense mass is too hard for the bullet to pass through. So very few bullets will bounce back. This is analogous to what Rutherford had inferred about the atomic structure. His first conclusion was that most of the space inside an atom is empty. This is because most of the alpha particles could easily pass through the atoms and hit the detector straight. Now, if most of the space is empty inside an atom, then where is the positive charge located? Well, that's the second conclusion. The positive charge is compactly packed in a tiny entity. This occupies an extremely small space inside the atom. Now, why did he think so? Let's go back to our cotton ball and bullet example. Can you recall the second and the third case? Yes, the bullets get deviated on hitting the tiny sphere of the edge, and they will rebound when they hit the center. Same explanation holds true for this. A few alpha particles get deviated. That means there is a possibility that these hit the edge of the positive center. Yes, And one more possibility is that they get deviated because the positive center repels the alpha particles as they're also positively charged. Also, a very small number of alpha particles rebounded. That means there is a possibility that these alpha particles had directly hit the positive center. But since the number of these rebounding particles is too small, it explains that the volume occupied by the positive center is also very small. If the space occupied would have been big enough, then the number of alpha particles bouncing back would also be greater. So let's say there are gold particles in the foil. He found that most of the rays pass straight through the atoms. A few rays change their path and get deflected. Lastly, very few particles bounce back. These results compelled Rutherford to come up with a new nuclear model. Let's have a look at the hypothesis put forward by him. Firstly, there's a positively charged center in an atom called nucleus. Nearly all the mass of an atom resides in the nucleus. Secondly, the electrons revolve around the nucleus in circular paths. Thirdly, the size of the nucleus is very small compared to the size of an atom.
So I hope after watching this video you are clear with the idea of discovery of proton and nucleus by Ernest Rutherford. Next is the discovery of neutron. We know that Ernest Rutherford predicted that there was a massive particle in the nucleus which was positively charged. In the year 1932, James Chadwick measured velocity of protons knocked out from the paraffin by an unidentified radiation from beryllium. This is a picture of how the apparatus for the discovery of neutrons look like. Let us now watch a video to understand the same.
Discovery of neutrons. According to Rutherford, the nucleus of an atom contained only protons, and these protons decided the mass of an atom. But we know that hydrogen has one proton in its nucleus, whereas helium has two protons. If the protons were the only particles in the nucleus, then a helium nucleus would have two protons and therefore only twice the mass of hydrogen. However, it actually has 4 times the mass of hydrogen. This suggests that there is some other type of neutral particle present inside the nucleus along with the protons. This mystery was put to rest when James Chadwick discovered neutrons in 1932. Let us now understand the experiment performed by Chadwick with the help of a flowchart. He placed a source of polonium in an evacuated chamber. In front of the polonium source, a thin foil of beryllium was placed. The alpha rays were made to hit the foil of beryllium. The beryllium foil emitted the mysterious neutral rays. Chadwick placed a target in the path of these rays. These rays knocked out atoms from the target. These atoms, which had become charged as a result of collisions, were made to enter a chamber filled with gas. These charged particles ionized the gas and the ions drifted towards an electrode constituting a current. By measuring the current, he estimated the speed of the ejected atoms and came to the conclusion that the mysterious rays contain particles having mass almost equal to that of the protons. Chadwick identified these uncharged particles as neutrons.
So this is the discovery of electrons, protons and neutrons. Now we move on to the next concept, that is atomic number and atomic mass number. Depending upon the number of protons that are present in the nucleus, it gives the chemical identity to that particular element. And this number is called as the atomic number of the element, and it is denoted by capital letter Z. We know that the atom is electrically neutral, and it is because it contains the same number of electrons in it as the atomic number. In simple words, we say that the atom is electrically neutral when it has equal number of protons and equal number of electrons, that is equal number of positive and negative charge. So if you want to calculate the atomic number, which is denoted by the letter Z, then the formula is atomic number is equal to number of protons, which is equal to number of electrons. The number of neutrons which are present in the nucleus is denoted by the symbol capital N, and the total number of protons and neutrons which are present in the nucleus of an atom is called as its atomic mass number, and it is denoted by capital letter A. If we want to calculate the mass number, that is capital letter A, then the formula used is mass number is equal to number of protons, which is denoted by capital letter Z, plus number of neutrons, which is denoted by capital letter N. Therefore, it is written as A is equal to Z plus N. If we want to find the number of neutrons, then N is equal to A minus Z. Let us understand how to calculate the number of protons, electrons and neutrons in a nuclide of argon. Here, the mass number, that is A, is equal to 40 and Z, that is number of protons, is equal to 18. So here we need to calculate the number of neutrons. So we are going to use the same formula, that is A is equal to Z plus N. Since we want to calculate the number of neutrons, we will write it as N is equal to A minus Z. So A is 40 and Z is 18. After calculating, we get the answer as equal to 22. So the number of neutrons in this particular nuclide of argon is 22. The composition of any atom is represented by element symbol X with the atomic mass number A as superscript written on the left and atomic number Z as the subscript. So here you can see how it is written. So the atom or nucleus which is having a unique composition, which is specified in this way, it is called as a nuclide. So the argon with mass number 40 and atomic number Z, which was 18, was the example of nuclide argon. The next topic is isotopes, isobars and isotones. First we shall study about isotopes. There are certain elements which exist as a single natural nuclide. For example, fluorine. Fluorine is a single nuclide having the atomic mass number 19 and the atomic number 9. However, there are many elements which exist naturally in two or more forms, that is, you can say as mixture of two or more types of atoms or nuclides, and this individual nuclides, they are called as the isotopes of that element. So how would you define isotopes? The isotope of an element have the same number of protons but different number of neutrons in their nuclei. We know that the proton number is only the atomic number. Here is an example of isotopes. So we are taking the example of isotopes of carbon. So carbon has three isotopes, that is carbon 6 and 12. So 6 is the atomic number. So you can see that that remains same, but the atomic mass number, that is denoted by the letter capital A. So here it is 12, 13 and 14. So it is differing for all the nuclides. The symbol for these nuclides are also written in terms of C12, C13 and C14. So as I told you, the atomic number which is denoted by the capital letter Z is similar for all the three nuclides, which is 6. However, the atomic mass number which is denoted by capital letter A differs for the three different nuclides of carbon, that is 12, 13 and 14 respectively. Now if we want to calculate the neutron number, then we are going to use the formula N is equal to A minus Z. So after calculating, for C12 we get the answer as 6, for C13 the answer is 7 and for C14 the answer is 8. The next column is regarding the percentage abundance, like how commonly it is present. So the first carbon, that is C12, it is present about 98.9%. Then C13, it is present very rarely, that is 1.1%. And the next is carbon 14, which is present less than 0.00017%, which is very lesser amount. And the next is the stability. So C12 and C13, they are stable, while C14, it is radioactive in nature. Next are isobars. The definition of isobars is the atoms of different elements, they have the same mass number but different atomic numbers. So basically the isobars, they are going to be different elements. Being different elements, they are going to have different chemical properties and also are going to occupy different position in the modern periodic table. Now here is an example of isobar. So here we are taking the two nucleides, that is of carbon and nitrogen. So the atomic number is different for the two. For carbon it is 6 and for nitrogen it is 7. But if we look at the mass number, which is denoted by capital letter A, it is similar, that is 14 and 14. In order to calculate the neutron number, we will use the same formula, that is N is equal to A minus Z. Hence we get the answer for carbon as equal to 8 and for nitrogen as equal to 7. In order to calculate the number of protons, we know that number of proton is equal to the atomic number only. So for carbon it will be 6 and for nitrogen it will be 7. The next concept is the isotones. The definition of isotones is the atoms of different elements, they are going to have the same number of neutrons in their nuclei. Here we are taking the example of boron and carbon. So if you look at the atomic number, which is represented by capital letter Z, for boron it is 5 and for carbon it is 6. The mass number, which is denoted by A, for boron it is 11 and for that of carbon is 12. In order to calculate the number of neutrons, we are going to use the same formula, that is N is equal to A minus Z. After calculation, we get the number of neutrons as 6 in both the cases, that is in case of boron as well as carbon. So isotones are those atoms of different elements which have the same number of neutrons. So this was all about the isotopes, isobars and isotones. Now we are moving on to the next topic, that is drawbacks of the Rutherford's atomic model. Rutherford had put forth his nuclear model of atom, and he said that his atomic model resembled to the solar system, wherein the nucleus would play the role of the massive sun and the electrons would act as the lighter planets. The electrons in this model, they could not be stationary because there is electrostatic force of attraction which is exerted on the electrons, pulling them towards itself. Now, stationary means the electrons cannot stay in one place, they have to keep on moving. However, the electrons that are revolving about the nucleus as described by the Rutherford also was problematic. Now, why was that so? We know that the electrons, they are negatively charged particles in the orbital motion. Now, as these electrons are moving, there is accelerated motion that is accompanied by a continuous change in the velocity of the electron. This means that this electron here, when it starts rotating, it is going to give out radiations. Since it is giving out radiations, means the energy of that electron is going to decrease. So it is going to follow the spiral path, and a point is going to come that this particular electron is going to fall into the nucleus. However, this is not the case in terms of atoms. Real atoms are stable, whereas this model was indicating towards instability of atom. So this was one of the major drawback of Rutherford's atomic model. The second drawback of the Rutherford's model was it does not describe the distribution of electrons around the nucleus and their energies. So basically, Rutherford's atomic model was not able to explain the stability of an atom. So these were the drawbacks of the Rutherford's atomic model.